All right, so in this video we're going to do partial fractions introduction. So I've got this integral here, crazy looking integral. What I'm thinking here is that I've got something that is factorable in the denominator. Turns out this is factorable, factors to x plus 2 times x plus 1. And if you try to do this problem, just straightforward looking at this piece right here, you get kind of stuck because you can't do a u substitution because there's no x in the numerator, right? And can't do one of your regular rules. Doesn't look like it's one of the trigonometric substitution problems because we're not dealing with any square roots or anything. So what we end up getting stuck with is this idea of partial fractions. And so the partial fractions, what's powerful here is we take this rational expression and we convert it into two more simple rational expressions where we know right off the bat that this would just be a times the ln of absolute value x plus 2, and then that would be plus b times the ln of absolute value x plus 1. Okay, plus c would be your integral. All right, so whatever that a and b are constants. Okay, so it really makes that problem pretty easy, and you can get this through a u substitution. If you substitute u equal x plus 2, then du is equal to, du is equal to dx, and so you end up with that a over u du. Or what do you know? The a comes out front, then you have the integral 1 over u du, which is that ln absolute value u. Plug in the u here, you get this right there. All right, so all that aside, let's talk about some more theory here. When we're integrating, so when we're integrating rational functions, we've got a couple options. All right, number one, if the degree of the numerator, also known as the top part of the fraction, okay, the degree of the numerator is greater than or equal to the degree of the denominator, or the bottom, then what's the case? We use long division first. Okay, so use long division first to simplify. All right, so an example where the degree of the numerator is greater than the degree of the denominator. If I had x squared plus 3x plus 2 divided by, well, golly, we know this factors, right? So if I divide by x plus 2 here, okay, well, what do I know it should equal? Well, if I'm dividing by that, it should equal x plus 1, right? You see how that simplifies the problem? Using long division, just a little refresher, x plus 2, divide out into x squared plus 3x plus 2. How many times will x go into x squared? 1x, so x times x plus 2 gets me x squared plus 2x, so I'm going to do x squared plus 2x, and then so don't forget to write what you multiply by up on top of this, and so draw the line, change the sign, and so that's 0, this is x, and then drop down the 2, so then how do I get x plus 2 from x plus 2? I multiply by 1, so I'm going to put that plus 1 there, and I have x plus 2, draw the line, change the sign, and I get a remainder of 0. So my answer is x plus 1 there. So just a quick rehash on how to do long division. If you need more help with that, you can go back to my college algebra videos, and I explain how to do that. Just go search for long division in the search bar for YouTube on the Clark way. Okay, so That's what you do if the degree of the numerator is greater than the degree of the denominator. That problem, x squared plus 3x plus 2 over x plus 2, that had a degree of 2. This one has a degree of 1. So the numerator was greater than the denominator degree. Now, if it's the other way around, if the degree in the top, we'll say top just to write it quicker, is less than the degree in the bottom, okay, then what happens? Then, if possible, only if this is possible, factor and use partial fractions. If it's not factorable, then don't worry about using partial fractions, okay? So we're talking about factoring it, all right, breaking it down. So the question becomes, how do you get what these numbers are? Is this 1, is this 2, whatever, right? How do we figure that out, okay? So let's take that problem there. 3 over x plus 2 times x plus 1 equals something, some number over x plus 2 plus some number over x plus 1. Now, how would I go about solving this? Well, the first thing that I would do with this rational equation is I would multiply through by the common denominator. And so I see I have an x plus 2 factor and x plus 1 factor, and then I have both of those things in here. So I'm going to multiply everything through by x plus 2 times x plus 1, okay? And so whenever I do that, whenever I distribute this through here, that's going to get me, let me rewrite this. Okay. I'm going to multiply everything by this, so that means I'm going to have it here. I want to write it over here. I want to have it here, and I'm going to have it there. Okay? So now what's going to happen? So this x plus 2 is going to cancel with that x plus 2. A lot of cancelization going on here. X plus 1 cancels with x plus 1 here. X plus 2 cancels with that x plus 2. And this x plus 1 cancels with that x plus 1. Make sure to cancel everything through before you do anything else. Okay, so now I have a times x plus 1 and then b times x plus 2. Okay? So it seems like it's a little bit easier. Now, there's two ways to go about solving this problem from here. All right? This way that I like to do is clever, but maybe not as obvious and straightforward, okay? So what I like to do is plug in values of x that makes terms disappear. So what would make something disappear? If I get a 0, right? So what value of x would make this first thing go to 0? Well, if I plug in, say, an x equal to -1, okay, into the equation here, what does that give me? That gives me 3 equals a times -1 plus 1 plus b times -1 plus 2. And so that's 3 equals, well, this thing goes to 0. So 0 times a, that's 0, okay? But then this gets you 1, so that tells me that b is equal to 3. See how that's easier than trying to solve, okay? And then the second thing, I would look and I would say, how can I make this term go away? If I plug in x equal to -2, I think I can make that go away. So x equal to -2 gets me 3 equals a times -2 plus 1 plus b times -2 plus 2. This gets me 0, and so that goes away to 0. 0 times b is 0. And so I have this -a equals 3. If negative a equals 3, then a is 3, negative 3. All right, just divide 3 by negative 1. All right, and so a is negative 3 there. So now I know what a and b are, okay? So what I can say is a becomes negative 3 and b becomes 3. So now I know what these are, the a and b, to make it equal. All right? And how could you check this yourself? You could cross multiply and add all this stuff together. And remember, with fractions, you got to get the same denominator, which happens to be this. And so once you go through that work, then you can see that this actually does add up to that over there. Okay? The other way to do this, all right? So another way that you can do this to get your A and your B. Well, the other option would be to multiply everything out. So I have ax plus a plus bx plus 2b equals 3, okay? Now, polynomials are equal to each other when their coefficients agree. So what do I mean by that? Over here, I have 0 x's plus a coefficient, a constant 3, equals, and now how many x's do I have? I have an a and I have a b for my x, okay? And then I have a constant of a plus 2b, all right? So all I did was I collected ax and bx together, and then I factored out an x out of that, okay? So I have the constants, the coefficients, and the constants there matching up with these here. So then what I would do is I would set up linear equations and solve. And so I would have 0 equals a plus b. Since this coefficient has to be the same as this if everything is equal, right? And then this 3 has to equal that right there. That 3 has to equal a plus 2b. So how would you solve this? Well, first I'd solve the easy one. I would say that a equals negative b. And then I would take that and I would do substitution and plug this in here. And so I have 3 and then negative b plus 2b. So b equals 3. And so once I know b equals 3, then this is negative, then a is equal to negative 3. Okay? And so that's how you can do it that way, if you want to do it that way. This way is more straightforward, mind-numbing. You don't really have to think about it. You just multiply it all out and then make sure that your coefficients on each side match up how they're supposed to match up. Okay, after you collect like terms. The other one, you look and you say, what value of x can I plug in here to make that go away? What value of x can I plug in here to make that go away? So you kind of have to do a little bit of thinking, but not too terribly difficult. So let's go back to what we had. So we had integral 3 over x plus 2 times x plus 1 dx equals, and then we said that it was negative 3 for x plus 2, and we said that it was 3 for x plus 1, okay? And so now all we have to do is use substitution. U equals x plus 2, du is dx. So what does this become? It becomes negative 3 over u du. And then the next one, u equal, and if you didn't feel comfortable using u, you could say v. So v equals x plus 1 to have a different one here. And then dv is equal to dx. And so this would be 3 over v dv, okay? And so the integral of 1 over u du is ln absolute value u. And I'm going to take that constant there, put it out front. Take the constant here, put it out front. Ln absolute value v plus c. And then my u is x plus 2. And my v is x plus 1. Okay? And so that is how you do it right there. All right? So pretty cool here. That's kind of the technique that happens when you're doing all these partial fractions. You end up with a lot of u substitutions for ln integrals. Okay, so you're gonna see lots of this going on here. Now, could get a little fancy here. They could say, okay, this is cool. Back of the book might be like, but this can simplify. And logarithm property says that this goes up into the exponent there. So I'd have ln absolute value x plus 2 to the negative 3. And then plus ln absolute value x plus 1 to the positive 3. So power rule, bring it up, right? And then addition with logs is the same as multiplication. So this becomes ln, that's a weird n. Okay, ln x plus 2 to the negative 3 times x plus 1 to the positive 3. And so then you could flip this to the denominator. And so you have x plus 1 cubed over x plus 2 cubed. Okay? And if you wanted to go even further, you could just say this whole thing, x plus 1 over x plus 2 all cubed, plus c, plus c, plus c, plus c. Okay? So don't freak out once again if you get this as an answer, but the back of the book says that that's the answer. Just know that, they did a little bit of algebra to combine the logarithms. Okay? So you might want to go back and look at your logarithms, properties of logs. If you do ln a plus ln b, this is ln a times b. If you do ln a minus ln b, this is ln a divided by b. Remember, logarithms are exponents, so it makes sense that multiplication is addition of exponents, same base, add the exponents. Division is subtraction, same base, subtract the exponents. Remember all those pretty rules. And then same thing if you have like a number 5 ln a, this is same as ln a raised to the 5 power, that power rule going up there. Okay? So, 5, it could be any number, whatever number you wanted in the front. All right. So in general, we've got some rules going on here. Whenever we do partial fractions, when you set up your A, B's, and C's and all that stuff, what you're looking for, say you have the scenario 1 over x times 2x plus 1 cubed, okay? This one is a little bit different. How's it different? Well, you actually have 3 factors of 2x plus 1 going on here. So to account for those 3 factors, we're going to build up the powers. So first factor, you can say, well, it's got that 1 over x thing going on, right? So I have some a over x, okay? Just like whenever I had the factor here, I had to account for that factor with some constant here, and then the factor here, I had to account with that factor with some constant there. So I'm doing the same thing here, plus some, well, it's a linear factor, so it's a b for the constant, and I have a 2x plus 1, and there's only one of them. We're building up the power as we get to build up to the 3, so we start at 1. And then we're going to build up another linear factor, but we're going to square it. So we're building up the power. We build it up until we get to the same power that we have here. All right, so you're building up. The reason I show you this one is so to let you see that you're not just creating an A and a B here. You need an A, B, C, D to build up that power from factor of 1 to a factor of 3. So you're accounting for all of those 3 factors going on there. Okay, so you can see here that you got 1, 2, 3, 4. That's 1, 2, 3, 4 different constants that we're going to need to solve for. So it can get pretty complicated pretty quickly. If you combined like terms here, like on this part right here, you would see that this would simplify, and you would get an A over X plus, well, this would be like B times 2x plus 1 squared plus C times 2x plus 1 plus D all over 2x plus 1 cubed. If you get common denominator before you add these 3 pieces together to get that. And so what you see here is you're building up the powers of each possible polynomial that has a degree less than the denominator. You remember, to be in partial fraction land, what did we say at the very first? We said that the rational polynomial needed to have a degree that was less than the denominator. Okay, if that's the case, factor if possible, use partial fractions. So a degree that would be less than a degree 3 term here would be a degree 2. So if we only had the 1 here, then we would only be accounting for constants degree 0. If we only had 2 things here, then we would only be accounting for the linear scenario of ABX. Okay, so the reason we're building up here is so that we can potentially have any possible quadratic, okay, degree 2 polynomial or less that would satisfy this equation here. Okay, so let's do one more of these just to make sure that we know what's going on, because there is one last case. Up to this point, we dealt with linear factors. Even though we cubed the linear factor, it was still 2x plus 1 is a linear factor. But here, we have a quadratic factor going on. So game is still the same for the first part. That's a over x. And then for the second part, this is going to be b over x minus 5. Why is it b? Well, because it's a constant term. Okay, it's a linear factor, linear factor. These are both linear factors here. Okay, but this one here, this is a quadratic, irreducible. So an irreducible quadratic factor. Why is it irreducible? If I tried to factor this thing here, the only way I could factor would be to be x minus I, x plus I. And I is complex. It's not a real number. So we're not dealing with complex calculus. Therefore, we're stuck with saying that this is not factorable. Okay? So since this is not factorable, we can't factor this into a linear term. We have to come up with another way. Well, what is it? A degree 2 here. So this numerator needs to be less than degree 2. Well, less than degree 2 is degree 1 or degree 0. These constants here are degree 0 terms. So we need to account for the linear. So I put a cx and plus a d in there. Okay? So that's what's happening. When you have an irreducible quadratic term, instead of just putting some constant like you did for the first 2 linears, you put a and you put b for those factors. With the irreducible, you put a linear, okay? So it's 1 degree less. This is a degree 1 term. This is a degree 1 term, so you put a degree 0 term in the numerator. This is a degree 2 term, so I put a degree 1 term in the numerator. Okay, so it's 1 less. It's less than the denominator degree. All right, so hopefully that's a good introduction on how partial fractions works. In the following videos, we're just going to run through examples of decomposing and then integrating